Hi, so in this video I want to do two things. I want to give you a geometrical understanding of the equation A inverse A equals I, and I want to show you a formula for calculating the inverse of a 2 by 2 matrix, and maybe also give some geometrical insight to that formula. You won't find that in the book because the book doesn't start with linear transformation, but we have this tool in our toolbox so we can use it in order to better understand what's going on. So if I'm talking about the inverse of a matrix, it's also the same thing as talking about the inverse linear transformation to a given linear transformation. So for example, let's say I have a linear transformation T1 of x, which is represented by the formula AX. Okay, so if it helps, you can assume A is 2 by 2 here. So the first column of A tells you where I is getting sent, the second column of A where J is getting sent. Okay, now I've got, so let's represent this in a little diagram. Okay, so I perform T1 and I get AX. So the inverse transformation is the one that keeps things where they are. Okay, so the transformation that I'm looking for here, T2, it's such that it's taking us back to X. Okay, so it, maybe I can illustrate it like this now. So I've got T1, AX, and I've got T2. Now you can assume, for example, that T2 is T2 here, it's the matrix Bx. So B, this would be sort of my B here. Okay, so I'm gonna get B AX. Okay, but that's gonna have to match the vector x, because remember, if I compose them together, I end up where I was initially. Okay, so the question is here, let's geometrically, what would be BA? Well, BA is actually the standard matrix of the composition of the two linear transformation. So it's T2 dot T1 of x would be BA times x. Okay, but when I compose T2 with T1, I'm going to get back x. Okay, so I could try to think, what is this matrix here? Okay, what's the standard matrix that represents the composition of T2 with T1? Well, looking at my equation here, I can tell that if I start with vector I, I'm going to get back vector I. Okay, again, because the output is x no matter what the input is. Okay, if it's x initially, it's x as the output. Okay, so if it's T of I here, the output is I. If I look at T of J, it's also J. And remember that I is the vector 1, 0, J is the vector 0, 1. So those are the columns of the standard matrix for the composition of T2 with T1. And that composition is the matrix BA. So BA must be such that its first column is T of I, and second column T of J. And the first column is 1, 0, the second column 0, 1, and that's the identity matrix. So it shows you that this matrix here, it keeps things where they are. And that's exactly what happens when you compose two inverse transformations together. So when you replace B by A inverse, you get A inverse A is I, because things will stay where they are because you're doing a composition of two linear transformations, and A inverse will also give us I, because once again, things will stay where they are. So when we have 2 by 2 matrix, okay, let's write it as A, B, C, D. The theorem 1.4.5 in the book says that there's a formula for the inverse of this matrix. So this matrix has an inverse if and only if, and there's a condition, if and only if AD minus BC is not 0. And I'll give some geometrical meaning to that equation here. Okay? And in that case, I can calculate the inverse of my matrix, and here's the formula. It's 1 over AD minus BC, which is non-zero because I assume it's non-zero, so I can divide by it. So this is something to remember, AD. So it's basically the difference of the products of the two diagonals. So there's the main diagonal and the other one. So you multiply AD together and then BC together, you subtract them. And then after that, you flip the elements on the main diagonal. So AD becomes DA on the main diagonal. You hit the other ones, the other components, with a negative sign, but you don't change where they are. So B stays where it is, but it's just hit with a negative sign. And that's your formula. Okay? So maybe an example. If I want to calculate the inverse of 1, 2, 1, 3, which is the matrix that was given to you in the previous video, is going to be 1 over 1 times 3. So that's the product of the main diagonal minus 2 times 1. And then you interchange the elements on the main diagonal. You hit the other ones with a negative sign. And that's it. You get your inverse matrix. Usually what we do is that we try to distribute this scalar here that stands in front of the matrix to the components of the matrix. But here we're kind of lucky because this is just 1. So the inverse is just 3 minus 2 minus 1, 1, which was the matrix that was provided in the previous example. Now, what I want to show you finally is that is an explanation to this condition here. Where is it coming from? Okay, geometrically again. Okay, so according to the theorem, we'll see that there's no inverse to this matrix when the corresponding linear transformation will send R2 onto a line. And I'll show you what I mean by this. Okay, so note ABCD has no inverse when the corresponding linear transformation squishes R2 onto a line. When is that going to happen? Okay, that's equivalent to saying that T of I, okay, where I gets sent, is going to be parallel to where J gets sent. That's the only way for the linear transformation to send R2 onto a line. When is that going to happen? Well, what's T of I? That's the first column of the matrix. It's AC, and AC will have to be parallel to BD. Okay, when are two vectors parallel? Where if two vectors are parallel, it's not too hard to see that that's equivalent to the area of the parallelogram that's formed by those two vectors, which is the norm of this cross product. Because when you calculate the norm of a cross product, you get the area of a parallelogram. So if that the two lines are parallel, the two vectors are parallel, the norm of the cross products, or the area of the parallelogram, will be 0. Okay, that's only going to happen if the cross product itself is 0, because if the norm of a vector is 0, it means the vector itself is 0. And if you calculate this cross product, you'll see that it's going to give you 0, 0, AD minus BC. So if the two vectors are parallel, the last component will be 0, so that the norm is 0 itself. So what's important to remember here is the statement that I wrote, which is when you have no inverse, it means that your linear transformation is sending R2 onto a line. So it's sending something that has dimension 2, because R2 has a basis of composed of two vectors, onto a line, and something that has a basis composed of only one vector. So it goes from dimension 2 to an object of dimension 1. And when that happens, you cannot go backwards. You cannot go back to something of dimension 1 back to an object of dimension 2. That's not possible. So that's why there's no inverse. There's no way you can come back. Okay? So in other words, our transformation, it goes from R2 onto a line. Okay? So that's dimension 2 here, but the line has dimension 1 because there's only one vector in its basis. You cannot go backwards. It's not possible. So no inverse in that case.